polynomial on C2, but it is polynomial on this set because it is equal to constant. And constant is polynomial. So it's a very bad example of a function which is not, it's regular function. So you can, quite often you can represent the same function two ways, regular and irregular, and to prove that something is not regular, it's not enough to represent it by a fraction. Another problem that people had, mostly you solved correctly. There's questions about how you have the continuous function which is polynomial. Sorry, you have continuous function, f continuous and rational. Then there is a question if it is regular, and then if it is regular on Cn. Okay, this is true, this is false. But not many people realized what is different between these two cases. The difference is that here you have the ring of regular functions is factorial. So this is true whenever the ring of regular functions is factorial. Otherwise, it might be true or false. What is true is that, in fact, so the implication is true if and only if you're on x, x is normal. So this is a criterion for normality of a variety. But it's sort of not obvious how to prove it. I didn't do it. Variety is normal if and only if all rational continuous functions are, well, rational bounded functions are regular. For instance, you have this.
Continuous rational bounded function
Is regular. Yeah, this is equivalent to being normal. So this is another example. Here it is bounded but not continuous, because you take a function which takes value 1 here and 0 here, and it is not defined there. So if, for instance, if you have xy equal 0, this is your cross, then you can take a function yeah, so let's have x plus y over x minus y. Well, yeah, right. So for for y 0, this is 1. For x 0, this is minus 1. So this is an example of a rational function on this variety, which has this property. It is bounded, but not regular. It's not regular because it's not defined in 0. And not continuous, obviously. Okay. Do you have any other questions about these solutions? Okay, so today I will start with trying to build, to produce algebraic, well, it's not hard to see that product of algebraic varieties is algebraic. What is slightly harder to see is to see why product of projective is projective. So this the first we start with this observation that product of projective is projective. Okay, so for that I would probably start with explaining that tensors have rank. So tensors have rank. So there is a way of defining rank, very like for all tensors. So rank of a tensor, which is some. So you have coefficient. You have a tensor, say t, tau. Inside tensor product v1 times v2 times and so on times vn. And you obtain it as a sum, coefficients, lambda I, and then you have v1 times v2 times and so on times vn, where vi belong to the space di. So we're interested in the rank of a tensor, and rank is minimal. K, such that in the sum you have k monomials. For instance, tensor x, tensor y has rank 1, or 0 if it is 0. There's, yes?
If we take a linear map as a tensor of type v star, it will give just a rank of a...
Precisely. Thank you very much. Yes, this is what I was going to say now. So you have now a matrix. Yeah, but first we should interpret homomorphisms from V to W as tensors, and this is the same as V star times W. So how you can see it? Well, if you have an element here, you can, so it's a, the elements here are sums of products. So lambda I, sum of lambda I times W J, where lambda I belongs to V star. And then if you have V, some vector inside V, you can take this V and multiply it by this sum, like here, lambda I W J, and obtain sum. You have here pairing V lambda times WJ. So, am I clear so far?
Professor, turn the monitor, please.
Sure. Okay. This gives you a map from this space to that space, because this belongs to W. The dimensions are the same, and it's sort of clear that if you have a non-zero, well, if you have a you write A from which is homomorphism from V to W as a sum of as a matrix Ij, where in basis Vi Wj, so Vi is a basis in V and Wj is a basis in W, then A corresponds to a tensor, a sum Ij. Here you have an element of dual basis, Vi star Wj. So this isomorphism is very clear. And then now you should remember what is the rank of a matrix. This is a maximal, it's a dimension of its image. And if its image is k-dimensional, you can write it in appropriate basis as like you take projection to a k-dimensional space, you take a base in this k-dimensional space, and you map this basis to some other basis in the image. And this is precisely rank. So this is precisely the rank of the tensor. Okay, but this was just for your information. I would just need only decomposable tensors for rank n. So definition, if you have tau inside V times W, called decomposable, if tau is V times W, where V and W are tensors in V times W. From this argument, it is clear that not everything is decomposable because, decomposable is rank 1. This corresponds to decomposable tensors under this isomorphism correspond to matrices with one-dimensional image. Okay. So who understands this theorem well? Good. Thank you very much. Okay, so I have this proposition. So I have a tensor tau inside V times W, and I interpret tau as a map from V star to W using this isomorphism. So V double star is V. Everything is fine dimensional, so this should be understood. Okay, then tau has a decomposable if and only if. Let's call this map tau 1, for instance, to distinguish it from tau. Tau 1 has rank 1. So one-dimensional image. Okay, so its proof is sort of completely clear. So proof, if tau 1, if tau has rank 1, tau is V times W, then it's clearly then tau 1 is represented by an appropriate base. So we take a basis which has V and W as its vectors. So tau 1 is represented by a matrix which has zeros everywhere except one place, Ij. Well, since its base is just 1. Conversely, if tau 1 has rank 1, an appropriate base is represented by such a matrix, and then tau is equal, for this basis, just a product of two basis vectors. Questions, comments? Okay. This is a reminder about algebraic cones and projective varieties. I would need it for the next slide, but it's just a reminder that if you have a C star invariant subsets in Cn plus 1 are the same as projective varieties in Cpn. So if you have X in Cpn projective, you have cone of X in Cn plus 1 C star invariant. Okay, and then if you have Z in C star invariant, you can take the corresponding projective variety, which is called projectivization. P of Z belongs to P of Cn plus 1, which is Cpn. It's projectivization of Z. This is something we had a lot. Questions, comments? And you have graded ring as well. So the graded ring should be small and not big. Graded ring is a ring of this cone. Regular functions on the cone. Okay. Moment. Yeah. There is something I... No. Yeah, there is a slide which is lost. I don't know what happened. Maybe it's later. I forgot it. Anyway, let me tell it without slide. So there is a claim. It's pretty clear anyway. Claim. The set of decomposable tensors tau inside V times W is affine variety. Is statement clear? So proof is very easy, proof. So you have tau represented by a matrix, Xij. Any tensor is represented by a matrix because it's, you just take a basis in V, takes a basis in W, and you identify tensors with matrices. Or you use this isomorphism between tensors and homomorphisms. And then rank tau is equal 1, and this happens if and only if all two-dimensional minors vanish. In other words, you take two-dimensional matrices inside this, and you compute the determinant. If it is 1, if it is 0, then rank is 1. If rank is 1, then it is 0. Okay, and this is algebraic condition. This is algebraic condition. Clear? Okay, but also this condition is invariant under, so remark. So this is the end of the proof. Remark. This set, let's call C of S. C of S is C star invariant. In other words, if you have a decomposable tensor, you multiply it by a number, it remains decomposable, right? Okay, then we can define using this previous S is its projectivization of the set of decomposable tensors. It's projective variety. Okay, called, so its definition, called Segre variety. Okay, it's written there, so maybe there was no slide, but I'm just confused. But is it clear so far? Please ask questions if something is missing. Yeah. Okay, we had a lot about products. So the products exist in just as a categorical notions. They are defined by universal property that if you have X and Y in objects of category, then amorphisms from some Z to X times morphisms from Z to Y is equal to morphisms from Z to X times Y. And you can consider this as a definition of product in category. In categories. Okay, and then what we had is that it works for affine varieties. So there is a theorem, which was, I mean, it's like lecture 9 or something, theorem, that if you have X and Y, affine varieties, then the tensor product, or X tensor product with OY. So you take the rings of regular functions over C is reduced, and corresponding algebraic variety is X times Y. In both senses. So it's a product in the sense of just taking products and taking regular functions some natural way, or it is a product in the sense of this notion. And this is easy because you just notice that if you have a homomorphism from a ring to something and from another ring to something, you have a homomorphism from their product, tensor product. So if you invert arrows, you will obtain something called coproduct, and tensor product is coproduct in category of rings, but then category of rings and category of algebraic varieties, well, category of reduced rings and algebraic varieties are obtained one from another by inverting arrows. Anyway, this was already done, and I hope it's clear. Good. Okay, in fact, you can extend this construction to category of algebraic varieties. So if you have X and Y algebraic varieties, you take a UI, Vj, affine covers of these two varieties. So it's certain finitely generated rings over C. Then you take UI tensor times Vj. This will give a affine cover of X times Y. And your gluing functions are just the restrictions of gluing functions from the transition functions are just obtained as by taking transition functions here and transition functions there and taking tensor products. So it works sort of tautological way. There's nothing to do. And you have your sheaf of regular functions. Sheaf is defined locally, so you need to define it only on here, and on here you have it because you can take products of affine things. So product is well defined. What is not quite immediately obvious that it is a categorical product. It's left as an exercise. So exercise, proof that this product is categorical product. It's not hard. I mean, if you have a map from Z to X times Y, you can just take projection. This would give you a map from Z to X. This projection is clearly algebraic, so it's a well-defined map. And conversely, if you have a map from Z to X and from Z to Y, you take a map from Z to a product and you check that it is algebraic map by looking in charts, because algebraic map is just map which are represented by regular functions in local charts. But you have it already in local charts that it is a product because you know that it is a product for affine varieties. Okay, the important thing is that Segre variety is product of two CP, two complex projective spaces. So theorem, suppose you have V and W vector spaces over C, and Z is space set of decomposable tensors in V times W. you can take its projectivization, then this corresponding projective variety is product. So I have PZ is projectivization of V times projectivization of W. Statement clear? Now, the proof is not hard. The idea is that we need to construct projection maps, right? So you take any linear functional, lambda from, say, V to C linear map. Non-zero, obviously. For zero, it's not interesting. Then you define a map psi lambda from this cone to W. Takes V times W to lambda of V times multiplied by W. This map is compatible with C star action. So this is a C star invariant map. So psi lambda is, I mean, if you multiply a vector by a number, its image is multiplied by the same number. So psi lambda is C star invariant. Okay, the problem is why it is not good enough to immediately, because it's not defined. I mean, it's defined on a cone, but some vectors it maps to 0. This is the problem about this map. And of course, if it maps some vector to 0, you cannot extend it to the projectivization, because if you want to have, if you have two cones, you can, and you have a morphing from one cone to another, it defines on projectivization only if the image is non-zero. If the image of something is 0, it doesn't correspond, it doesn't give you any line. Okay, but it is independent as a map from the set of vectors in V, such that, so let's consider the affine chart. A lambda inside V is a set all V, all vectors V inside V big, such that lambda of V small non-zero. So on this chart, this map psi lambda defines a map A lambda to projectivization of W. Because here it's non-zero, it's well defined. But it is independent on lambda from choice of lambda, because if you, if you change lambda, this would just be multiplied by a number. It would stay in the same line. So as you make a transition from one chart to another, the map doesn't change. It remains the same map. So this gives a map, well defined now, because it's you just, for each point, you pick a chart where it belongs, and you use this map. Defines a map from Segre to projectivization of W. Okay, and the same way, of course, you define a map from Segre to projectivization of V. We just need to prove that this is an isomorphism. So this is step one. Step 2 is to prove that it is an isomorphism. We need to invert this map. So this is defined, is called PW, and this is PV. And invert is actually easier. So if you have, so step 2, invert the product of this map, pi W times pi V, or pi V times pi W, better in this order. You have V times W inside Segre, inside the cone. But let's take inside the cone of Segre. And then this gives you, oh, sorry, I'm doing wrong. So you have V inside V big, non-zero. So we just remove 0. W inside W small inside W big without 0. Then you take, let's call it, say, is there any notation here? No. Let's call it zeta from VW to Z. Just you take VW and map it to V times W. Okay, now we can predictivize. And then you just take a line generated by these vectors, because if they are non-zero, the product is non-zero, so this is non-zero vector, this is well-defined. This map is well-defined, first, and second, it's obviously it's invariant under C star action on this argument and on that argument. So it's well-defined as a map. So zeta is a well-defined map from predictization of V times predictization of W to predictization of Z. It's polynomial it's just polynomial. I mean, it's given by polynomial, and it is inverse to what we already have by construction. So there's nothing to prove essentially. Do you have any questions, comments? Good. Okay. And this gives us a corollary which is sort of expected. So corollary. If you have X and Y projective, then X times Y also projective. Okay, so proof. By construction, X times Y is algebraic subvariety in Segre S, Segre, which is equal to product of two projective spaces. So to see that it is projective, we just need to prove the following claim, that an algebraic subvariety of something projective is projective. The point is that algebraic subvariety is defined locally in Zariski topology, and projective is defined globally. So it remains to prove the following claim, that if you have Z inside CPN algebraic, then Z is projective. Okay. But in fact, we will do the same for the cone. So you have cone of Z inside Cn plus 1. This is also algebraic. I mean, this is also algebraic subvariety because I mean, locally cone is just a product of C star and your subset. So this is also algebraic. Algebraic means that it is locally defined by equations. You need to prove that it is globally defined by equations, then you are done. How you do that? Well, we already had it. If you remember, we had this proof that if your function is locally in Zariski topology regular, it's globally regular. Here you have the same. So locally in Zariski topology, this subvariety, well, we don't need it to be C, just any subvariety. So let's call it X. Algebraic. And I'm going to prove that it's affine. So locally in Zariski topology, X is defined by equations. By an ideal, say I. And then we take a cover by affine subsets. So UI corresponding cover. And each UI is Cn plus 1 without a d. Hi, where hi is regular, dhi is zero divisor of a regular function. Okay. Then the corresponding ideal, which is finally generated. So I restricted to U. I is finally generated ideal in the ring. You take polynomials and you invert this hi. This is the same as OUI. Okay, but then we have to remember that altogether, HI is a cover. So they don't have any common zeros except maybe 0, but anyway, I'm doing some. I'm just overstepping slightly. You have to fix this proof because I'm proving for affine, and we're applying to this to a cone which is without a point. So please fix it yourself, and I'm not bothering with it now. It's not hard. So what you have here is that you have this a cover, and then you have a, since the zeros of this HI don't intersect, you have a form, sum of the following form. This is something we already have. GI, HI is equal to 1. Because the ideal generated by GI doesn't have common zeros. These divisors don't intersect. Okay, and then you have your generators, like F belongs to I. It's of course not regular, it's here. But then you multiply F times sum from GI, HI, some very big N. It's F. And this is already regular. Okay, and this this allows you to globalize this. So you have something which is locally. Last time we have a function which is locally regular. Prove this is locally regular, globally regular. The same is true for ideals. I'm thinking this argument is may be confusing, but you shouldn't care. I mean, it's anyway, it's obvious, right? Just think it over. I'm not going to spend much time on it because to do it correctly, you need sheaves anyway. Lots of sheaves, coherent sheaves and stuff. Okay, let me give you another example. Well, now it's not a variety, but an algebraic map. It's called projection. So maybe I should start here. So we have a variety. Just a hyperplane. So definition, H inside CPN hyperplane, which corresponds, so you have CPN projectivization of V, and H is projectivization of the hyperplane. So this is V is Cn plus 1. It contains W, which is Cn and Cn. This is what is called hyperplane in complex projective array. It's complex projective manifold. Again, then we take X inside. Well, we take P outside of H. So this is a point in CPN without H. Then we define a map projection from CPN minus n without P to H, defined as follows. If you have some X inside CPN, it's a line. It's a line in V. We take a two-dimensional space generated by X and P. It's always two-dimensional, so this is without P. Then it is two-dimensional. And then we intersect it with H. So it cannot belong to H because P doesn't belong to H. Then this intersection has to be one-dimensional. Is a line. And this line, so the projection is it denoted some pi? Pi of X is this intersection. XP intersected with, oops, sorry, not with H, with W. H is this projectivization. So why it is projection? This is because, say, you have a point, you have this, like you can think of it as infinite plane or something. And for each other point, you connect these two guys by CP1, because projectivization of this is CP1, and you intersect this CP1 with this hyperplane. This is why it is projection. Make clear? And this map is regular because it's you can write it explicitly. So let me prove it. So claim pi is regular. Proof. There's nothing, in fact, to prove because it's sort of immediately obvious that it is given by polynomials because, I mean, all linear algebra is given by polynomials. But so at some point you think it automatically that you won't even ask yourself why it is polynomial. But right now, let's just give a proof. So, okay, I think I confused W and V. On slides, it's opposite. Okay. So you have V. This is our hyperplane here. Is a kernel of mu, where mu is a linear map. So it belongs to W star. I mean, every hyperplane is defined as a kernel of linear map. It's not a big deal. Okay, now you have for any x inside W without this line generated by P, the corresponding, you can write explicitly pi of x. So pi of x is kernel of mu intersected with a two-dimensional plane generated by x and P. And then you can write explicitly this intersection pi of x. I'm passing now to affine coordinate from projective. So it was no longer a line, but now a point in that line. If we pass to affine coordinates, this means that we replaced line by chosen point. And then it will give in these affine coordinates just mu of x times P minus P, mu of P times x. If you apply mu to that times P, you obtain 0. This belongs to intersection, and the map is polynomial. So it's polynomial in affine coordinates where you represent x by a vector. Clear? Good, thanks. Now I remind you about Veronese curve. It's something we had last time. So the idea is that, okay, maybe we should make a break now before next day we'll go to quadrics and it will continue to the end. So you have 5 minutes until 14:25. If you have questions, comments, you want to ask me about your test work, coordinates, projective coordinates on CP1. Okay, then you put the point xy to a point x square, xy, y square in with these projective coordinates in CP2. This is called Veronese map. Well, there are more Veronese maps, but what I claim, and it was proven last time, I'm not going to repeat the proof. This is embedding from CP1 to CP2. Yes, and the image is defined by equation y square is equal xz. Well, a b square is equal ac. Because the product of these two is precisely the square of this. Okay, this is something we proved. Here the proof is written, but it's computation. I don't need to do anything. And I'm interested in a general class of hypersurfaces which are called quadrics. So definition, suppose that you have a bilinear symmetric form, G bilinear symmetric on Cn. It defines you what is called quadratic form. G of xx is called quadratic non-degenerate. So if it was non-degenerate, this is called non-degenerate quadratic form. Do you know this? That there's a bijection between quadratic forms and bilinear symmetric guys? Good. A non-degenerate quadratic form. Okay, quadric in, so let's call it n plus 1, in CPN is a subvariety given by g of x equals 0. This is homogeneous polynomial degree 2. And I will assume non-degenerate. So it's sometimes you consider degenerate quadrics non-degenerate, and then you say, okay, this is non-degenerate quadrics. So sometimes I will indicate that it is non-degenerate because sometimes it's important. Okay, the first observation is that all quadrics are isomorphic. So claim all quadrics are isomorphic. Okay, suppose you should know this. How you prove that? Non-degenerate. They assumed non-degenerate. It's assumption. I assume that all quadrics are non-degenerate. So how you prove that? You have your non-degenerate quadratic form, bilinear symmetric form. You take an orthogonal basis where it is diagonal. Then you have another quadric, you have another orthogonal basis, you just map one basis to another basis. This maps one quadric to another quadric. So the idea is that proof GL n plus 1 C acts on quadratic forms, non-degenerate quadratic forms, transitively. So it maps any quadric to any other quadric. Okay, now we can have some examples. So we don't care which quadric we take, so we can take any. So the first example is zero-dimensional quadric. So example, zero-dimensional quadric is 2 points. Proof. Okay, all quadrics are the same. It doesn't matter which one we take. So take x, y equals 0 in CP1. This is union of x and y. So it's x equals 0, and so it's like union of 1, 0 and 0, 1. Right? Clear, right? Should be clear. And this quadric is non-degenerate. Of course, you can take another quadric, but all quadrics are equivalent, so it doesn't matter which one we take. Okay, now claim one-dimensional quadric in P2 is isomorphic to CP1. Okay, this is because this is quadric. It is Veronese curve. So you have this Veronese curve obtained by this embedding. It's clearly CP1, but then it is given by quadratic equation, which is non-degenerate. And then all quadrics are equivalent, so they are all CP1. In fact, you will see the explicit map very soon, which gives this equivalence. But on the other hand, we had it in the previous slide. Questions, comments?
Professor, what is the action of GL n plus 1c over the
Because you have, so what is non-degenerate symmetric, what is the symmetric form? So you have sim 2 of V. It's a subset in V star times V star. So the bilinear symmetric forms are just subset on bilinear forms. This is a tensor. And the linear group acts on all tensors. So GLV acts on V star times V star. And the action is by this change. So here you have two quadratic forms. You find special bases where they are the same, and you act by element of the group which maps one base to another. This maps one quadric to another quadric. And the same action, by the way, it's an action on polynomials as well. So if you have some polynomial equation or algebraic projective subvariety, in Pn you can always act by linear map, and it would give you another projective subvariety. Because the same reason that the group of linear transform acts on not only on symmetric 2 forms, but on n forms. And symmetric n forms are precisely the polynomials of degree n. Okay. More questions, comments? There's another nice group-like observation that not only not only the general linear group acts in exchanging quadrics, but then you have a stabilizer. So if you have the definition O of V is subgroup of general linear preserving a non-degenerate quadratic form. And now claim. So if you have Q defined by quadratic form, so it's a quadric, then GL, so quadratic form say H, then O of VH acts on Q transitively. So quadric is a homogeneous space. Homogeneous space is a space where you have transitive group action. So to prove it, it's a pure linear algebra. Do you know this already? So the idea, for instance, in fact, there's a more general statement, but it's proven. What I'm going to prove it is part of it. So if you have a set of vectors of square n, square r, then the group acts on this set transitively. It's like a sphere. You know that on a sphere, group of rotation acts transitively. So this is like a sphere of radius 0, but the same is true. So let's prove it. To prove it, you start with you have vector v inside VB. In fact, it's true. It acts only not only on the quadric but on its cone as well. So I will prove even on vectors. So you have non-zero vector, a non-zero mu of g of VV is 0. And then we know that our quadratic form is non-degenerate. Then there exists W inside V such that G of VW is non-zero. First, I want to make W square 0. So I write for that W1 is equal to V mu V plus W. I want that G of W1, W1. Of course, it is equal to 2 mu G of VW plus G of WW. I want it to be 0. This means that mu is equal to minus G of WW divided by G of VW times 2. This is okay because we know that this is non-zero. And the new W1 will have the same property because V square is 0. So if you multiply it by V, this would give the same number. And then I would rescale W1 in such a way that you have G of VW1 is equal 1. And I have this matrix 0, 0, 1, 1 of this quadratic form. G restricted to this space, VW is this matrix. In fact, over complex numbers, if you have non-degenerate quadratic form, it always has this form. This is something we have discussed. I mean, it's non-degenerate, so you can always assume it has this form. So it's not surprising. Okay, now the orthogonal complement is well defined. And it is orthogonal complement because this is non-degenerate subspace. So orthogonal complement doesn't intersect. And we can take an orthonormal basis and orthogonal complement. We obtain a basis, where, so it's like V, W, and then you have Z1 dot, is it Z here? Z1 dot Zn, such that G has this form 1, 1, 0, 0, 1, 1, 0, 0. Good. Now you have two such vectors. You do the same. And then you just put a map from one, I mean, the bijection between these two bases, V to V prime, W to W prime, Z I to Z I prime. It will be an isometry because the quadratic form has the same matrix. And it maps any given V to any given V. This is why it is transitive. Okay, and then we have a corollary that the quadrics are smooth. Corollary, Q is smooth. Well, we know that one point is smooth. This we know. This is something we proved, I don't know, lecture 17. That any algebraic variety has one smooth point. Okay, but then all points on a quadric are the same because there's a group which transitively acts on them. So if you have one smooth point, the rest are also smooth. You just move this point to the other point. Clear? Good. Now let's discuss what happens. Yes. First, notice that what is birational geometry of quadric? So all quadrics are rational. This would be actually an argument which proves that in dimension 1, quadric is just CP1. The same argument will prove it. So claim. Let me define rational variety first. So definition, X inside CP1, well, just X algebraic variety is called rational if X is birational to CPN. So the first trivial example is Cn, birational to Cpn. I mean, they are equal up to a divisor. And you know that if two varieties are become equivalent after removing divisor, they are birational. Okay, now claim or theorem, is it proposition? Proposition. Quadric is rational. And proof is very easy. we have quadric Q. We have a point on it X. So this statement is actually true for over all fields, not only over C. But it assumes that a quadric has a point. So it is false precisely when a quadric doesn't have a point, and then it is not rational. But for obviously by Hilbert Nullstellensatz over algebraically closed field, such as C, every variety has a point, including quadric. For characteristic 2, it's not clear what is quadric, because quadratic forms are not the same as Bellini symmetric forms. So you have to you have to redefine quadric for characteristic 2. Because I mean, we implicitly assume that everybody knows what is that Bellini symmetric forms are the same as quadratic forms. It's false for characteristic 2. So. Okay. So it has a point Z. Consider projection. Projection from CP. So we assume that our quadric sits inside CPN. CPN without Z to CPN minus 1. This is projection which we defined just a few slides ago. Then, okay, as we have just discussed, every in dimension 0, every quadric has 2 points. So this means that if you have a subspace, so let's CP. This would be projectivization of. Do we have here some notation? No, we don't. Good. So it will be projectivization of V, and this will be projectivization of W. Okay. Now we take a two-dimensional space generated by Z and something X inside CPN. Oh, sorry, inside W, because it's a high vector space. And you have your quadric. So it's defined by H or by G here. H. So you restrict H to this, Z and X. And for general subspace, this is 2 points. 2 points. One of them is Z. So there is another point which you can actually write explicitly by taking H and dividing it by the form vanishing in Z. Lambda, where lambda of Z is equal to 0. This is degree 2. This is degree 1. But this is divisible by that because, I mean, this is everything, it's on CP1. So it's just polynomials. And if this one, degree 1 polynomial, this is degree 2 polynomial, it divides by that. So this is regular degree 1. Okay, so the idea, you have some quadric, every 2 points, every general line intersects this quadric in 2 points. 1 point is fixed, another moves around. So your projection is takes this point to that point. And it is 1-to-1. Is 1-to-1 generally on Q. This is our stereographic projection. If you remember, you have a sphere, you have its pole, and then you project everything to a plane. The important thing is that this is 1-to-1 over C, and this gives you generally 1-to-1 map, and So it's actually invertible. You can invert it very easily because if you have a point on Q, this clearly gives you its image is well defined. But then if you have a point on your plane, you pass a line through this point and your point Z, and you take another intersection point, which is defined by this equation. So inverse map is also algebraic. Am I clear? Good. Of course, it's not entirely good. I mean, it's not well defined because it's possible that this would be degenerate. Then it's just the whole CP1 belongs to your quadratic. It's quite possible. I mean, if you have a non-degenerate quadratic form, it can be restricted to some smaller subspaces as degenerate. Because, I mean, just suppose that z squared is 0, x squared is 0, and they intersection, and they are also orthogonal. This might happen. But this never happens for small dimension. If you have two-dimensional space or three-dimensional space, then you don't have any like subspaces for which this is 0, two-dimensional subspaces. This means that when your Q is one-dimensional and the ambient space is three-dimensional, this map is actually like stereographic projection. It's everywhere defined. It's everywhere well defined, and this is the explicit way of building this isomorphism which we obtained from Veronese. So for dimension 1, it is given by projection, and it is really one-to-one. Okay. Now let's work in P3. So it's not hard to see now that for two-dimensional quadric, so you have Q inside CP3, two-dimensional quadric is isomorphic to Segre subvariety CP1 times CP1 in CP3. So which corresponds to corresponding to C squared times C squared is mapped isomorphically to C4. So you have precipitation of this is CP1, CP1, CP3. So proof. Okay. Now we work with that, right? So our tensor has our space has two dimensions. It has so a tensor in C squared times C squared is given by square matrix. By square matrix Aij. Okay, and Segre is zeros of its determinant. Is zeros of determinant of Iij, and this is the same. This determinant is the same as I11 squared. Oh, sorry, I11 I00 plus A11 A00 A10 A minus, sorry, A01. Right? This is a formula for determinant. But it's quadratic form, non-degenerate. Nice. So we obtained that Segre is just given by in that dimension is given by a single equation which is quadratic. Not degenerate quadratic, and we're done. Now I have like 5 minutes. I will just show you some pictures which illustrate this thing. But it's a picture which, I don't know how much you know this stuff about affine quadrics in R3. Did you do that? So who did that already in like undergraduate or graduate? No one?
Yeah.
Okay, you did. So you know this.
Analytical geometry.
Yeah, it's part of analytical geometry. Precisely. So you can do this. We did it over complex numbers, but you can do that over reals. And over reals, it's natural to work with affine quadrics, which are determined by this equation. So affine quadric is subset in R3 or Rn, but we are interested in R3, given by Q of V plus lambda of V plus C equals 0, where Q is quadratic, lambda linear. Then this covers ellipsoids, and this covers cones. Have a cone, and then you have where a signature, since it's three-dimensional, we assume it's non-degenerate, signature of Q is 1, 2, 2, 1, which is the same up to a sign, and then 3, 0, and 0, 3, which is also the same up to a sign. So we'll be interested only in this non-determinant, and for non-determinant you have only two choices. This is hyperboloid one-sheeted or two-sheeted. I'm not explaining this, but it's just definition. You define one-sheeted for C negative, two-sheeted for C positive. And it's sort of easy to see that one of them has, this doesn't intersect the plane, so it has two components. This intersects, and we shall see that it has only one component. Anyway, on R2 quadratic forms, zeros of quadratic form are just union of two lines. There's nothing. This is something we just discussed. It's just on R. I put it here because so that you can see it's obvious. Now the main point about hyperboloid. The hyperboloid is ruled. So suppose you have one-sheeted hyperboloid, and you intersect it with the tangent plane. So H in R3, one-sheeted.
One-sheeted real hyperboloid.
Yeah. It won't work for other. T X H, it's tangent space, tangent plane. Then T X H intersected with H is quadratic, again affine quadric, but it doesn't have any constant term. So if you look at this equation for affine quadric, C here is equal to 0. It's not hard to see. Then it is union of two lines. So this is union of two lines. This is what I explained on the previous slide. There is no time, but it's true that if you have a quadric without constant term, then just union of two lines. Or one line. Anyway. So this is ruled hyperboloid. It's really, this is what happens, in fact, the same happens in over complex numbers. You just can't draw a picture. Because over complex numbers, what happens is that you have a quadric inside CP3. You take its tangent plane. And you intersect this tangent plane with the quadric, and you obtain a quadric in smaller dimension. But then it will be again a union of two lines, which are distinct because otherwise it will be singular. And it's generally, it's definitely non-singular. And then since it's, anyway, you obtain two lines, and these two lines correspond to this decomposition. So this is quadric, is a union of two lines. I think I have just, okay, yeah, you can also prove that if you have rotate a line around another line in CP, in R3, you obtain hyperboloid. And conversely, I mean, all hyperboloid with symmetries are obtained like that. And I'm not going to, I mean, it's part of your analytic geometry course anyway, but just to remind you. And in the end, you have this lots of more pictures. So what happens is that you can start, you have two families on hyperboloid, just like on complex numbers, you have two families of lines. And it is a union of each of these families, but so if you have a line from the first family, like here, it intersects every line in the second family just once. This gives you a parameterization of hyperboloid by, it gives a coordinate. So you have two families of lines. They are both parameterized by lines, because each of this family intersects another line precisely once. So you can just project your hyperboloid like there to, like, let's forget about the second family. Then you project your hyperboloid to the CP1, which is parameterizes these lines. And then you realize that you can just take another line from the family, and this would give you parameterization. Okay, so this was the quadrics. I think next, we don't have much less lectures left, right? Something like 2 or maybe 3. So I will, what I would do now, I would try to prove that if you have projective variety, then algebraic map image is always projective. Which is, I mean, we never did that. And it is in fact false for if you do with affine. For affine it's false. So this is really advantage of projective geometry over affine.